11.3 Acids and Bases Reaction. Let's look at 11.3. This is the last part of the lesson, and in fact, this is just acid base, or should I say neutralization? Okay, neutralization stoichiometry. That's all it is. Okay, so nothing here different aside from the fact that we're now, for our double displacement reaction, we're using an acid and a base. That's it. Acids and bases. Okay, produce salt and water. Understand that a salt is any ionic compound. So an ionic compound is considered a salt. Okay, so an ionic compound is considered a salt. And again, this is just review from chapter 5 back in unit 1. Okay, so now when we think about a neutralization reaction, and we think, okay, if I've got an acid and I put a base, it'll neutralize, it'll make it salty water. But understand that the concentrations of these acids and bases play a very big role in order to, in fact, get that true neutralization reaction to actually, in fact, take place. So that notice that here that a balanced chemical reaction for an equation shows that really 1 mole of nitric acid reacts with 1 mole of sodium hydroxide that we see in this example. Okay, so it works out to a 1-to-1 ratio. Now, if we have equal molar concentrations or quantities of nitric acid and sodium hydroxide, we can, in fact, get our neutralization to work out to pH value of 7. Okay, but understand that if we use a strong acid and a weak base, we're not going to get that 7 value. That we are going to need to make sure that the concentrations, those mole ratios are going to be, in fact, used properly to help us figure out that a neutralization will, in fact, take place. So we might have to figure out what is the concentration of that base, or what volume of that weak base do I, in fact, need to truly get a pH value of 7. Just because I have an acid spill and I decide to throw any base on it to try to neutralize the spill, right? If I don't have the correct amount of that weaker base, let's say, to use for that, so I'm not going to get that neutralization to actually take place. Okay, so understand that the mole ratios play a very big role in getting a true neutralization. So remember, understand that reactions between acids and bases of different strengths usually do not end in a neutral solution in terms of pH value. So identifying neutralization reactions. Most neutralization reactions, no visible sign that a reaction is actually occurring. Okay, so you would use, so if you were to pour an acid and a base together, you're not really going to see anything. Okay, it's not until you use an indicator, an acid-base indicator, that you'll determine whether or not a neutralization, in fact, did take place. Okay, understand that most acid-base indicators are weak monoprotic acids. Okay, so what happens is the dissociation. So when a dissociation, in fact, occurs, that's where we have the so-called color change in that neutralization reaction, right? Because all of a sudden, like, hey, we're going from one thing to another, but there's a dissociation that takes place to give rise to that different color. Okay. Let me, I thought I had it in here. We talked about this before, right? Phenolphthalein is an indicator used for bases. I mentioned that I do have I had students create a demo using the phenolphthalein with acids and bases, typically in a titration reaction. Titration reactions deal with us putting drops of a base into an acidic solution to see at what point does it neutralize. Okay, and so we typically will use phenolphthalein in there because phenolphthalein has a really cool pink or fuchsia color when dropped in a base. Okay, so when we put a drop of phenolphthalein in an acid, we don't really see any change in color. But we put it in a base, and all of a sudden that solution of that basic solution will in fact turn pink or fuchsia, whatever you want to call it. So let's look at some sample problems here. Again, these sample problems, double displacement reactions. Okay, you need to be able to put together your double displacement reactions. Okay, so anyhow, we've got hydrochloric acid. So we've got this volume of hydrochloric acid to neutralize this volume and this concentration of sodium hydroxide. What is the concentration of hydrochloric acid? Okay, so there are the answers. Anyhow, let's go to the steps. So step number 1, write out your balanced chemical equation. The AQs matter. And here there's no precipitate, but that L we write in for water, because typically if we have aqueous, it's considered a no reaction. Anyhow, we've got these values here, so we substitute that here, or we throw it in there to find our N value. Using that N value and using our mole ratio, we find out that the number of moles are exactly the same. And so we use that value for our C value with the volume, okay, as we have here. Okay, so we take the number of moles that we found using our mole ratio divided by the volume that we were given. Notice milliliters to liters in order to use these formulas, and we get this value here at the bottom of 0.1806. You'll see here this warning, do not use this formula, because this formula is only if you have one thing, an acid or a base, and you're trying to neutralize it. That is it. Okay, here we, not neutralize it, scratch that. If we've got an acid or we've just got a base and we're trying to dilute it, okay, we're trying to dilute it. So this is only for dilution. Okay, when we are weakening a very strong substance and trying to figure out how much water should I include to lower the concentration value. It is never, ever to be used in a stoichiometry problem. In a stoichiometry problem, you are to use this C is equal to NV. Some understand that, yes, you might come across a question and you do it and you're like, hey, but sir, I use this formula to get the answer. Well, it won't work with something like this one, okay, because the ratio is not a 1-to-1. Just because a ratio is 1-to-1 does not mean that you can use this equation, because you using it implies you don't quite know when to use the proper formulas for a stoichiometry problem and for a dilution problem. Okay, so please, please, please do not use both of those, or do not use this equation unless it's for a dilution. Okay. And the second sample problem, really no different. So we've got sulfuric acid reacts with potassium hydroxide. So sulfuric acid, potassium hydroxide. Here's our salt. Here's our water that it produces. Again, just shift the two metals, right? The metal in here is H. Metal here is K. So switch the K with the H, and you're creating new formulas. Remember that the new formulas you create are based on crossover rule. If you can't put this together, okay, if you can't put this stuff together, you are missing valuable information from back in Unit 1. So please go back to the Chapter 5 of types of reactions, how to put together formulas, how to put together the reactions in Chapter 5, and then go back to Chapter 4 on how to put together ionic compounds. Okay, and again, I stress this warning to not use that C1 V1 equals C2 V2 formula. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.